Hey, let's take a look at the encryption schemes that we have seen so far in the lecture and kind of just recap what happened. The first encryption scheme that we took a look at is the one-time pad. And that's a really easy encryption scheme where you just take your key, which is a uniformly random bit string, and then you just XOR it with your message in. This thing is secure against all possible eavesdroppers. Doesn't matter how much computational power they have, just information theoretically, like stochastically, you could say, this value here, the ciphertext, does not give any information about the message at all. It's independent of the message. However, the downside of the one-time pad is that the keys need to be as long as the message. So the length of the keys are as long as the message. And we also can't reuse the keys, which makes this much worse. We can only use every one-time pad key only once. Meaning that if we wanted to encrypt multiple messages, we would have to have multiple keys. Each key needs to be as long as the message. So this is problematic in reality. Then fueled by this nagging key length that we had here, we came up with a way of compressing keys, kind of. So the idea was that maybe we could just store a short key, and then as soon as we want to encrypt something, we can just stretch it to the length of the message. And this is exactly what we did when we came up with the PRG-based encryption. So there, the scheme is essentially the same, but now instead of using the key k directly, we first stretch it using the PRG, so that we have the short key k, and then we make a big random string out of it using the PRG, then XOR the message with that. Then this is secure against not all eavesdroppers anymore, because as we have seen, PRGs can be broken by exponential time adversaries, but those should be secure against PPT eavesdroppers, so adversaries that only run in polynomial time. Which is obviously worse than the one-time pad, which was just secure against all of the eavesdroppers. However, the key length now is much better, where depending on the expansion factor of the PRG, our keys may be much shorter than the messages. So for example, if we have a PRG with expansion factor 2n, then the length of the keys is just half as much as the length of the messages. And as we will see later, PRGs with much larger expansion factors are also easily possible. So now we can have rather short keys and then very large messages. However, we still can't reuse those keys, because as before, as soon as we reuse the same key k, then this effective key that we have here, that we XOR with the message, will also just be the same both times. So if I encrypt the second time, this PRG value will be the same. And so then we get the whole problem with the one-time pad again, where we can know the distance between the two messages. So then we took a look at this. So, okay, we can't reuse keys. This is kind of unfortunate. So let's fix this. And then we came up with the PRF-based encryption. And this one was where the ciphertext there are just like this. So here we choose a random R, which is a uniformly random bit string. And then we evaluate the PRF at that position and then XOR that value with the message. Now the nice thing is, let's say we never use any of those R's twice. Then each time we throw a new R into this PRF here, the PRF will give us a uniformly independent, random-looking value, kind of like a one-time pad key, and then we can XOR that with a message. So now we can reuse the keys, because with every different R, we will get a completely different PRF value, and then XORing that with the message will make it secure. The only thing that we need to take care of is that we never use the same R twice. Because if we use the same R twice, then again, this part, the PRF part, if we use the same R twice, we have again the standard problem that we had in the one-time pad when we reuse keys. But we choose R from 0, 1 to the n, so the probability of ever seeing a collision can be negligible. Then what is this thing secure against? It's also only secure against PPT adversaries, because similarly to PRGs, any adversary that has unlimited runtime can easily break it. However, we did get a much better security model, which is CPA security. And now for the first time, we actually allow the adversary to see more than one message. More than one ciphertext on messages that he can actually choose adaptively. And this is a rather strong security model. We will see one that is even stronger than this later, but for now this is pretty good. It's much more realistic than eavesdropping security, because in reality, usually you would be able to make someone encrypt a certain message. For example, if there's a web server running somewhere, I can probably send him a request so that he needs to answer in a certain way to me, and then I can kind of control what he will encrypt with the key. The key length for this scheme is also just the length of M, so the keys need to be as long as the messages, but there will be ways around this later. In particular, because we can reuse keys, this isn't as bad. Because essentially we can take any long message and split it up into smaller messages and then encrypt it with this scheme. Actually, you've seen this, I think. It's the ECB mode. So this is it for our overview of encryption schemes. This is what we've seen so far. We will see one more in this line of schemes, and then we basically have covered all of the basics for symmetric encryption. Thanks for listening. See you in the next tutorial.